Going on, chat? Let's get to it. Huh? Let's do it. All right, so where were we last week? Let's pull up the PDB spec. So last time we worked on the this one. All right, so what's it zoomed in? There we go. I like that better. All right, cool. So let's see this one. Let's do it. Let's see. All right, cool. So now with that, we have this done. We might want to add something here for that. And then the other thing that's weird was that let's make a note on that on the README. Actually, let's not do it on the README. Let's just what was it? It was the sequence number can be negative. I think was the one, or no, the sequence number. Yeah. Okay, cool. Yep. We need to update that for the other types today. All right, so let's make sure this still compiles. Cargo test. Cool. All right, let's see. So we need to go to records mod. Yeah. Because now we need to be able to handle the all right, then we need what? Yeah. Cool. All right, so I think the one thing we probably need to go through and correct is the sequence number, which we keep saying is a U16. All right, let's make a commit first, actually. Oh, git restore. Okay, get status. see, can I put that right there? Yeah, there we go. Cool. So we don't need to do that one. The crystal record might. No, it does not. Yep. Cool. I think the secret is I guess I could probably just use like a ZellaJ split instead, so yeah, there we go. What did I just do? Okay, cool. Okay, cool. Okay, cool. Can I do vid mappings? Yeah, okay, cool. That's fine. Great. All right, cool. So now we can do tests and validate that everything is working. Refactor, Sucres. Right, so what if we just did like a RG seek mod residue? I'm reading that right? Like 22, 20, no, 18. Yeah, I think it's a I16. I think Sonic had this right. Yep. Okay, cool. Okay, cool. All right, cool. Okay, cool. I think that's good enough for that right now. Okay, cool. Hey, how's it going? Today, we are working on a protein data bank parser. Yeah, so I think we can mark that as complete then. I think that's right. I th- what is a protein parser? That is a great question. Thank you for asking. So in some of the biotech spaces, we have a standardized way for storing how things like proteins are captured and put into a file format. So that's known as the protein databank file format. There's other ways to do it, but protein databank is kind of common, and the reason for that is if we go to like RCS PDB, I think. You can basically look up a bunch of different proteins. So like we can look this up. You get the structure of various things like this. And basically the protein databank, there's a couple different ones. This is I think the Royal Protein Databank. So in the UK. I might be wrong about that. No. Yeah, this one I don't think is. But basically, you get a bunch of these different files that are called PDB files, and they kind of look like this. Let's see. Yeah, tests. What MBS? Yeah. What is the purpose of this parser? So the purpose of this parser is to provide a full coverage of the spec. So one common problem that the ecosystem really kind of struggles with when we talk about biotechnology is there's a bunch of projects that all need to parse these files, and all of them generally have to re-implement how that is parsed every time. Which is problematic because then what happens is they'll generally pull in other like larger programs to handle that parsing. So in this case, we're going to write a way to parse them so that they can be used for other programs, and that's the goal. We're not going to use it for anything else other than to actually handle the parsing itself. So the goal is to provide a stable implementation that someone can build on top of. With the eventual goal of being a drop-in replacement for some of the other parsers that are being used. So you get multi-threaded performance, which is pretty uncommon from when we're talking about parsing in biotech. So we get multi-threaded parsing because we're going to use Rust, and then you wrap it in Python. So you get all the multi-threaded Rust parts, and then it just copies to the GIL when you need it. And that's kind of the goal, is provide a really stable, fast backend for parsing these files. So scientists can just use it, and they don't have to worry about the performance of parsing it. It's just really fast. So it's not really calculating it. This file basically holds all of the data, and we're just going to put it into a more usable format for scientific software engineers, or research software engineers, rather. Are you using something like regex to identify the world that you're looking No. So one thing that's really interesting is the PDB spec was actually built for punch cards. So there's a couple of things about that make it very interesting. So the first is that all lines are never longer than 80 characters long. And they have very well-defined fields. Now, there's a couple exceptions to that, and that's like basically just from fracturing inside of the industry, inside academia. But this is basically, we have this spec that says like these are what the columns are and these are what it is. And so how we do all the parsing is because we know where all the positions are, we don't have to do regex at all. But that is how it's traditionally been done in the past. But instead, we can do we can look at the atom record because it's kind of the most important one. All we do here is that's a little hard. So all we do here is we just like parse this out using direct, like we just slice the string. And then we trim off the parts and then parse out what we need. And then that way we're done. But yeah, that's kind of the goal. So yeah, we don't use any regex because we know where everything's already going to be. So we don't need to guess. And then that way we can have like a really good control over our allocations. And actually, this is not the first pass of this project. So the first pass of this project was called Sonic, written in Zig. And if you look, they have a very similar way of doing it. So when we did it in Zig, we had a similar idea of like, okay, well, we'll try to do it, in a similar format, and then we don't need to rely on using regex or some other way of parsing. We can just know where the bytes are and pull them out directly. There was some work to initially look at this and try it out using like a parser combinator and use it that way. So kind of build dynamically. I don't think that we really need that in this use case, but I think that for the other, what if someone doesn't have the same position in your DB, have actually, yeah. So the primary goal is to use it as a Python library eventually, but it will also function as a crate if you want it. So you get both. But the thing is that the protein databank has a standardized file format, and all of the positions are always the same. That is the spec. Like, and the programs that don't adhere to that spec are generally pretty clear on what they're not. And the one that's interesting is actually the Atom spec does not. This handles a couple edge cases that are not standard, which are mainly alt location. Nope, that's not it. Yeah. So like charge information is not generally stored. Yep. Yeah. So they use a standardized format to represent any protein that gets captured by the protein databank. Yep. It's a pretty common format to use when we're looking at structural simulation. Now, so admittedly, this is kind of the older version of the spec, and the industry's kind of moving away to it. They're moving to a new format, and you might have seen this when I pulled this up. There's this other one called MMSIF format. We can pull that up as well. So the MMSIF format is, or otherwise known as PDBX, is supposed to be a replacement of that format. And it uses dynamic parsing instead. So it provides like basically headers, like directives that are then used to parse where everything is. So that's kind of the big difference. But the older formats, which are still where a lot of things get done, are done using this like 80 character format that's been around since like 1970 or something like that. So not necessarily that the proteins are structured in the same way, right? Because they might all look different, but like how the like what's in that, like what each line represents is always going to be the same. Thank you, I appreciate it. Yeah, the goal is to just provide a simpler way to do this. One big problem that we have in biotech and kind of how we're working on like some of these structural computing problems is that we run into an issue where there's kind of like everyone is kind of rebuilding the basics every time. There's a great project actually that I recommend for synthetic biology. Let's see if I can pull that up. Oh, let's see. Yeah. So this project is called Poly. Tim Stiles wrote it. And basically, it's a similar idea, but for different kinds of files. So it's a Go parser for handling like DNA sequencing and stuff like that. So it's kind of more on the genetics side, genomics. And that's what he does. And his stuff has kind of really inspired me on more of the structural computing side of biotech. So yeah, definitely would recommend checking it out. It's a great library. It's very well written Go code, and yeah, it's very cool. Okay, cool. So I think we're in a good spot. I just need to see what we have left. Um, let's see. We have a. Oh, okay. Let's see. All right. So what do we need to work on? Oh, we're working on these ones. So the DB reference ones are kind of weird. Let's see. DB ref 1 and 2. I thought I already had these, but maybe I don't. Yes, there's the standard and then there's the modified ones. Hmm. Okay. All right, so all right, let's remember how to type today. Source. I guess we can just put it all in here. I mean, they're technically different, but not really different, right? Because the standard format. Okay. The updated 2-line format usually does not fit in the space allocated. This includes genband sequencing, extension numbers greater than 12 characters. Please tell me they give me an example of this. Okay. But yeah, Pythagore, feel free to stop by the Discord. I'm actually part of the Caravan Discord with DM Mulroy, and some of the guys over there, like MetaMe and stuff like that. Um, yeah, come stop by, say hello. A lot of different languages, but we'd definitely love to chat with you. So come say hi. All right. So I think we could call this like dbrefx. Yeah, thank you. I appreciate you stopping by. Oh,
That is
Dylan.
wild.
Dylan, my guy. Thanks for stopping by. How was Gleam? Oh, Gleamel, my. Oh, Gleamel, my Gleam. That's awesome. It was great. Big fan. Yeah, I love Gleam. It's so nice. Like I said, there's a couple things I wanna get that I don't like about Gleam with like building CLI applications, but other than that, Gleam is great. It's very fun. I wanna learn enough Gleam so I can like help on the LSP. Admittedly, I think that'd be cool. But Yep, that's exactly right. Yep. Yeah, so when I started doing the essentials of compilation in it, and it's great, right? Like it's very fast, it's cool. And I'm like, how do I just build a REPL? Like I'll just, write a little REPL. And you can't really unless you're gonna, also ship a JavaScript runtime. And I'm like, yeah, we're not doing that. We're not gonna get that happening. But yeah, I do think it's nice. I think it's definitely like I do like it. Now, the one thing I will say, Dylan, is that when I started writing Gleam, I was like doing a lot of translation from your OCaml code for that. And the more I looked at it, I'm like, I actually like OCaml syntax, but like Gleam is so much easier to read, but I really like OCaml at the same time. So I'm kind of like 50-50 on it right now on both of them. So I don't know. We'll see. But um, what are we working on tonight? So, Chad, I was just explaining this. For those of you it's your first time here, um, my name is Ninjatron. You can find me over on the Discord at the Caravan for sure. But we are working on a protein databank parser. And what does that mean? That's a great question. So protein databank files are a standard file format used by scientists all over the world to store protein structure. So the information of like where atoms are in a protein. And that data gets captured, and then generally, sometimes it's crystallized, sometimes it's simulated or whatever. But it's used as a way to store where atoms are and kind of some of the relationships between them, but not all of them. So this kind of format. Now that data gets stored in what's called a PDB file or a protein databank file. And I can open one of those up. Tests 1MBS. So this is a protein databank file. And what it is basically the textual representation of these proteins. And it has information about like where it is and like what kind of atom it is and things like that. So what is that? Why do this, right? Why build this file? First of all, it's really fun. There's a couple things that are really weird about protein databank files, namely that they were built for punch cards and only support 80 character lines. And so as a result of that, you have some really interesting parsing constraints that make optimization very cool. Secondarily, the biotech industry has a hard time with a lot of them need these files, but every time they write a new piece of software, they're either pulling in a library that's huge to do this work, or they have to rewrite it from scratch, which often leads to bugginess and performance issues and things like that. So this project aims to provide a stable way for people to import and use these files, and it gets out of their way. They don't have to think about it anymore. So we are going to we're going to write Rust to do this for a couple reasons. The Rayon crate is really great. And with Rayon, we get multi-threaded interpreters or iterators. So because of that, we get multi-threaded. And then there's a great library called PyOxide, which allows us to write native Python bindings from Rust. That gives us a really, really solid performance gain because we don't have to like directly interface with the global interpreter lock. So by doing this, we can do all the computation, and then whenever it needs to be accessed, that's when we copy over to the GIL. So the goal is we're gonna do that. We're gonna provide kind of an interface that is usable for people who want to write in Rust, but we're also going to provide an interface for people who use Python, which is still kind of the standard in biotech. And we're going to have fun along the way. We're going to write it, and we were just kind of working through the spec. Into Nappy for JavaScript with the same base. Yeah. Oh. Why have I know this name? GitHub. Yep. Yeah. Exactly. And so the goal is to just provide a really rock solid base. So the targets I am definitely going to hit Python for sure. Nappy potentially. I'm more inclined to say ship Wasm. And that the goal is also it needs to be able to compile the Wasm. The other one is that. So we have this here. So Python for sure. Node maybe. Wasm definitely. And then the other one is Julia Rust. Nope, that's not it at all. Julia Rust bindings. Yeah. So I'm considering adding support for Julia as well. But yeah, so the goal is just provide a really complete, rock solid base of the whole spec, and then we'll build on top of that. Other people can iterate on top of it. Yeah, I think it's pretty fun. But keep it simple. It's like what I want, but I want very complete, very accurate parsing that's very fast. Thank you for the follow. I appreciate it. This project is actually the second iteration of it, although more complete now in Rust than it is in Zig, but it was originally written in Zig. And admittedly, I miss Zig so much sometimes, but I did all of this initially in Zig, and we've translated it to Rust and gotten way better performance just because of the concurrency that you can get out of Rust, which has been really cool. So we are going to do here we go, dbref 1 and 2. See, can I zoom in here? There we go. Okay, cool. All right, so we need to parse these two columns, or these two lines, and generally they are together because it's a 2-line variant of this thing. So I think ideally... does not fit the page. Okay, so there's always going to be two DB1 and like a DB1 and a DB2. Yeah, so it's like this. So if that's the case, then the record itself is going to be one record. So all of this will be one, but the actual line parsing is going to be separate. All right, so let's take a look at this. So that really means that, what do we need? ID code. Chain ID. So char. Pub. Insert. If I can spell, that would be great. Insert begin optional char. I think that's optional. What character is that? 20. Where did I miss it? What is that? Insert begin. 19. Yeah, right there. So yeah, that's optional. Okay. Now we want sequence end. It's also an I16. That's another optional char. All right, so I think in this case we have. Okay, so Genbank is one, but is Unimez another one? All right, what are the two? Oh, it's in the same file. Yeah, there we go. Okay, so database, the ID code. We have a chain ID. DB ascension. It's a string. And we have yep. And no, that's not right. Sequence end. Are these the same? So sequence 46, 55, and 25. Yeah, so 55. Okay, so these are going to match. That gives us a point of validation too. Because basically, so what this spec is saying is that they have these sequence numbers here, which are the start and end of where this record is, I believe. I think, or where the database is referencing it. You have a start and end on these, and it's like these numbers, and these match. So that's really nice. Oh yeah, that's very cool. It's a very common thing. Um, yeah, we use BioPython. Yep. Yeah. So, um, actually, we can look at that, and we can kind of show why, like, what the difference is. PDB. Can I turn this on? There we go. Okay, let's see. The PDB. Yep. All right, let's skip that one right now. I'm not feeling that. Can I just please look at the source here? Yeah, exactly. Exactly. And that's what I kind of want to show. Let's see. Yep. PDB parser module. Feels like a biology person who designed it. Exactly. So, if we look through, here, we create an object. That's great. We get the header and the trailer. Yep. Parse. Okay, cool. So, to start, which is good to know that I actually need to look into older format specifications. But we parse the records, and it literally is just looping in one at a time, stripping the new lines, doing a counter, these kind of things. And it's similar, right? It's slicing, doing the strips, um, and whatever. It's storing it, but there's some issues where you run into this. The biggest one being that you're kind of limited by Python itself. So you kind of run into the issue of you don't have control over your allocations. So how do we work through this and how do we fix it? Yeah, it's slow. And to demonstrate how fast this one is, yeah. Let's see. Records. Let's see. Um, cargo run dash dash features parallel. Yeah. Okay. So let's see. Yeah, and that's extremely common. We don't need to print the records. Let's just time them. So let's go through. We'll parse it 10 times. We'll do that. All right. I think that should be. Yeah, we need this too. Okay. So we'll look at the 1MBS file, which is I believe, if I remember correctly, is a pretty. Oh, that's one of the smaller ones. ls-alh tests. Yeah, so we do they're generally small PDB files, but it's decent. So we'll do 4PTH. Okay, cool. So that's the largest one I have. So we'll do it in parallel. I don't know why it's printing those out, but yeah. So we just parsed it, I think 10 times. Yep, 10 times. And you get under a second for each parse, and that's using like across. It scales across threads too. But even the single threaded is quite fast, but multi-threaded is kind of where this comes into play. So we could parse the whole file and do whatever we need. You just get it all in memory, and then you're done. You get it all structs, and then you'll get Python bindings as well. So this is not using CUDA. Let's be very clear. This is all CPU compute. And actually, CUDA with Rust can get a little out of hand, from my understanding. Yeah. Yeah. So CUDA has some issues in Rust, from my understanding. It still has some stuff going on, but it is growing. A lot of your CUDA is still going to be CRP++. Some SIMD. So that's the advantage of Rust. Is you do get some of your SIMD optimizations under the hood. For parsing. That was one of the things I was adding to. Yeah. No worries. But SIMD was something I was going to add to this project when it was still written in Zig, because Zig has really good SIMD primitives. But that's kind of the next goal. I think we could probably optimize some of it. I'm not sure how yet, and I don't know enough about SIMD to really do anything with it. Mm-hmm. Yep. So there's and we actually have git checkouts Python bindings. So there's PyOxide, which is a pretty cool project, or Pyo3. And its goal is to provide native ways to write Python bindings in Rust. So you can like name a function as a Py function and as a module, and then you add the functions, and then it makes it really easy. It's really easy to do. The hard part I'm trying to figure out is like the packaging stuff, but that's more of a Python issue than it is a Rust problem. But to kind of show you that, we have basically here. This is kind of messy, so just bear with me. We have ways that we can actually write Rust code, and it does all the parallel processing, like all that CPU multiprocessing I was talking about. All that happens under the hood. You get all that in Rust, and then whenever the nice part about PyOxide is it'll do everything in Rust multi-threaded. And the only time you need the global interpreter lock is when you go to access that data. Am I using Tokyo? No, not at all. Nope. There's no reason for this to do async in this case. We're using Rayon for multi-threading, which Rust. All right. So nope, not that either tonight, or that one. There we go. So Rayon basically provides you with parallel iterators. That's what it does. So it'll just scale to the number of cores you have, and then you get to use the iterator primitives. So to demonstrate that, we can look at main. If we have parallel, yep, yeah. So if we go to here, we do a parallel iterator. We have to iterate through it once single-threaded, but only through the objects that we create. We don't have to actually iterate through the file, so that's a lot faster. So this is all happening in memory. But basically, that's just to correct a edge case where serial numbers are not to spec. But in this case, what we do is we can do a parallel iterator over all of the lines in the file and maintain their order, because they only are order dependent at the end. So it does the parallel for loops basically, and then now we get all the records parsed out, and then at the end you get one vector of records, and then you're done. And then you can access all the fields that you want, and that interface kind of looks like this. I'm not even going to demonstrate how slow it is in OpenMM. Yeah, OpenMP. Why do I know that name? Like OpenMPI? Yep. Yeah, it's very similar. Yep. Yes. Yep. But the difference between this and like using something like an OpenMP, yep. Yeah, for C++. Yeah, so the difference between that is to show you the difference between implementation. All we have to change, so this is PDB reader single. This is like the implementation here. Basically, all we have to change is the iterator. So this just gives us a single-threaded iterator. If we want to use a multi-threaded iterator, we just have to put a parallel. We collect the lines first and then do parallel. That's it. Just 2 lines different, basically. So and that's admittedly why I switched from Zig to Rust in the first place. So Zig was great. It was very fast. It gives you a lot of flexibility. Running on Linux and Windows would run a bit slower. I think so too. Admittedly, that's not the use case I'm really planning for, but I still think my goal is still to just beat Python, right? That's kind of the goal. But I bet it will run a little bit slower on Windows. The goal would be ideally, so the goals are just like read write lock bug revealed by some random dude on Reddit. Really? What did that look like? Like what happened there? Is that just like it's doing repeated like reads? They couldn't report it. Oh, interesting. So how we kind of get around that is we do one read of the file up front, which is this here. Like if we're in a parallel case, if you're doing it single threaded, each line is read one at a time. Oh, interesting. That's interesting. So we do when we do parallel processing is we have to read the whole file in at once. So you read the whole file in and then you split it up that way. Yeah, this is. I'm not surprised that there's no way to report Windows bugs. That or there, if there is, it's like some weird process. Yeah, yeah, yeah. I'm again not super surprised that there's some bug that like just doesn't get caught because Windows. But yeah, my yeah. There's a reason I haven't written code on Windows unless I have to, which I haven't in a while. Yeah, most of your long-term computations are going to probably happen on Linux, and especially since like for this use case, like my exposure to this kind of came out of computational chemistry, and like their simulations are, you're talking about multiple GPUs for months at a time. Um, and so this is like the smallest part of that process. Um, yeah, those take time too. I heard. Yep. Yes. Yes, they do. They take a long time. So in this case, this is just really fast, and then we're good. But a lot of times you're going to run on a some sort of clustered environment, whether that's Kubernetes is becoming kind of more popular with that, but a lot of it was like Slurm kind of traditional high performance compute scheduling. So think like kind of supercomputer architecture. And if that's the case, so my goal with this, right, is like just provide a really easy way for this part, right? Like understandably, like reading in the actual structure is like the least important part. I mean, it's important. It's really important, but it's like kind of the part that's not doing a whole lot, but it needs to work every time and it needs to be consistent, right? So that's why building some of these basic tools is really important when we talk about that. Worked in a lab where they used to use PlayStation 3s to leverage the SIMD chips to save cache. Is there something I don't know about PlayStation 3s having really good SIMD chips? Hold on. Let's take a look at that. No, not the Sims. Sims. Let's see. I find it wild that the original PlayStation ran a MIPS processor. That's insane. Let's see. The synergistic processor unit. 128 128-bit general purpose registers. Interesting. That's wild. I find that really interesting because like a lot of the modern consoles use a very almost like standard chipset. Like they're very, like simple processors. That's fascinating. I'm gonna read more into that. I'll have to take a look at that. Yeah, so folding a home uh is a great project. Admittedly, in my new role, I work with some of the scientists that work on folding a home. Um, and yeah, they absolutely do use some of these programs to do it. One of which that I was actually kind of like highlighting So we look at like test.py. So OpenMM is a common molecular dynamics library, and it uses it does protein parsing, or it does more than that. It does like simulation work, but they use that as a core for open or folding at home. So yeah, that's like this is like the smallest part of that. This where we'd use that for part of that process. Yep. All right, cool. We're gonna hop back into it here in a second, and just kind of get this rolling. Get checkout main. Get stash. Hey, thanks for the follow. I appreciate it. And we just hit our goal of 130 followers. Thank you, chat. I appreciate all of you. I appreciate all the time that you guys take to come hang out. It's much appreciated. Cool. All right, so let's set a new goal, I think, yeah? I think that's in order. Thanks for the follow. I appreciate it. Can I just do this right in chat? Let's see. /goal. Let's do follower goal. Follower goal. Thank you. Start a new goal. All right. The goal now, we're going to push to 150. All right, let's start it. There we go. Yeah, and like I said, a lot of you came over here from Dylan's stream. I'm also over at the Caravan. You can check me out over there, and I have notifications as well. Feel free to stop by. I'm around pretty frequently, so feel free to come by and chat. And I'd love to hang out, and I'd love to talk weird file formats with you. This is the first one. I have plans to parse karaoke files, but we'll down the line. I have research to do for that. All right, cool. So let's take a look at this, right? So where were we? So we were looking at the dbref files. Okay, so this is going to be the refx record, which is good. Does it? Oh, man. Let me get a new one then. Maybe I got the wrong link. I will update that. But thank you for... I need a general purpose link. All right. Let's try that one. Wait, is that the right one? Yeah, there you go. I think that should be the right one. Actually, yeah, there we go. That's the one I want. There's a new link. Cool. Okay. Let's use this one instead. I will update that on. That one should not have an expiring. So you guys should be able to use that one. The new one. I will update that in Nightbot tonight. Okay, cool. All right, cool. Okay, so we have all this here, but we need to be able to handle the line parsing. So this one's going to be weird because it's a 2-line format, which is unlike all of the rest of them. Let's see what it said. Isn't it missing some fields? Is that really all of them? Database ID code. Database ID code here. Yeah, that hallucinated. Those do not exist here. Let's see. ID code 7 to 11. Yep. 12. This is, yep, 12. 15 to, yep. Oh yeah, because it's optional. So we have to trim parse on that. No, that's too weird tonight. All right, we're gonna change up these vibes. The music tonight is not it for me. Let's see. There we go. Okay, so we have the database. We have the ID code. Great. Chain ID. Yep, we get that. Sequence begin. Insert begin, which is optional, so that makes sense. Sequence end. Insert end. Yep. Okay. So it's 48 to 67. Okay, so what is this then? 29? DB Ascension, the Ascension code. Okay. Um, ooh, this actually presents an interesting problem. Because this one we might not be able to parallel process then. Admittedly, I don't think it's going to be that big of a problem. Yeah, it's in the header. We could probably single thread the header and then process the rest. Okay, I'm going to need to think about that, but let's think about how we're going to do this first. Okay, so we get the database here, which is 26 to 32. Yep, cool. Sequence database identification code, left justified. Yep. Here. And so that's not right. We'll come back to that. So it's going to be 48 or 47 to 67. Yeah, this one's going to be a little bit more complicated, I think. DB ID code we have. Chain ID we already have. Yeah, second line. Ooh, this is going to create a really interesting case. That's also completely wrong. It's a 19 or 18 to 40. No, no, this is not MySQL. It's protein databank files. This is what we're working on today. There we go. Okay, cool. So that should be done. Now the problem is this is not. We're gonna have to do like a whole. Am I gonna have to do a whole rewrite of this to like handle basically the header parsing separate from the body parsing? That honestly might not be a bad idea, honestly, because you could probably do the header parsing single threaded and the rest of it multi threaded. Because we need to preserve order and we can't ensure that if we're gonna do Okay, so that builds the record, but we don't have a way to parse that into a record. Like from a line. How am I doing that right now? No, we don't want that. We want lib. There we go. Sorry. All right, cool. So we have lib here, right? Record try from. So let's look at that. I have a way to do this, but I don't like it. But I think for the time being, it'll work. We can combine them at the end. All right, let's close this out. Let's get the spec back up. Um, okay, so I think what we'll do instead is we can break this apart. So we'll do DPL dbref 1 record. I forgot he did a cover of this song. Got a little more up for you guys. All right, so we'll do that. And we'll redo this to basically break them apart and then combine them later. Database ID code. Yeah, like that. I really need to reorganize this. We'll do 2. Sequence begin. Oh, I totally said that wrong. It's not ascension. It's accession. Did I spell that right on the other one? Yes, I did. Okay, cool. Okay, so we have the accessors here, and then what we'll do is we'll re-implement this, and then we'll just combine them at the end. Okay, cool. All right, let's see if I can get it. Yep. Okay, cool. And then we'll do the second one. And then we can use the same formats. We can do impl from string. And then what we'll do is we'll do impl combine. Or no. So then what we do is we can modify this record to then take L1, which is a DV ref 1 record. We might run into some cool lifetime stuff for this. All right, did I get it? Why is the accession? No, that's wrong. That's wrong. That's completely wrong. That's a string. Okay. Yeah, so I think that's probably the way to go. Is there like a I guess the from trade is the closest thing, but yeah. Okay. So I think then from the parser perspective, oh, I did not add that here. Yeah, because I added the sec. We forgot to add that one. I'm curious. Rust enum string. Yeah, okay. Oh, and I just slept my machine. Nice. Happens too frequently. All right, cool. All right, cool. All right, cool. So we have that running here. Okay, so now what we would add here is the mod.rs. Okay, that's where we are. And we want the okay. So there's the two DB references. And then we got to do these. Here. Okay, so I guess then we also need the DB ref x. Wait, I'm curious about something. Let's go look at something really fast. Yeah, that's what I thought. Okay, so what's interesting here is that these serialize into the same thing. Um, so we can actually do. We don't need this. Um, okay, so then what we can do instead is where did I put that function? Yeah, okay. Okay. So I think then what we can do is we'll use from here. So we'll do impl from, and we'll say a tuple of and then this is what we'll do here. Um, DB, oh, and then we'll do that here. So where was that before? DB dot That's not right. It's value. I think we can do this in 0 as well. Oh yeah. Do we have both? A DB ID code and an ID code? I guess so. Okay. Weird. I might have to dig into that one a little more, but right, so then we'll just use this one instead. I think these are supposed to be I16s as well, because they're sequence numbers. Yep. Yep. Okay. Yeah, so that's kind of cool. And then how would that look in lib.rs? Let's think about that. Hmm. So what I'm thinking is this, but I don't like it. But yeah. No, we don't want to check that. We're gonna say like if um hmm. Yeah, I don't like that either. I'm gonna put this here for right now, but I'm gonna change this. Ret records dot filter. Ooh, we want to enter mute. Filter the record if can I see like records dot contains? I don't want to do contains though. I want to basically what I'm trying to do is I want to get the records. Let me say record. Um, um, man, like basically what I need to do is once we have all the records, we need to then take the individual ones and like combine them into proper dbref records. So I'm guessing what we'll do is we'll say, okay, we take the records. Hmm. Hmm. Let me think about this. I guess we'll filter the elements. Yeah, so we'll say let db ref x equals hmm. Expected reference this a value of vec record from iterator is not implemented for vec record. Okay. Well, let's just try. Why do I need to do a map? Why don't I just filter it instead? So So now we have just those records. That's not exactly what we want because we need to do it in place though, because like we're gonna basically like, hey, grab this one, find the matching one, and delete them, and then call it a day. All right, I might have to think about that one and come back to that. Interesting. Well, that throws a whole wrench into things. I guess let's just find someone to raid. And I will be back later, either on Monday, maybe tomorrow. We'll see. Probably Monday though. Oh, let's raid Bad Cop. There we go. Twitch. Raid Bad Cop. Make sure to say hello. Bad Cop's reading the Bash reference manual today. All right, cool. Let's hit it. Thanks for everyone for stopping by. I appreciate it. And see you over in Bad Cop. See you.